Hello. In the last class, we introduced the concept of translating systems with springs and then with dampers, and then we looked at developing equations of motion, right? And we talked about a standard form of writing this, wherein you have all your system parameters and your system variables showing up here on the left, and anything that's external to the system showing up on the right. And then we kind of introduced this idea of degrees of freedom, where we talked about the minimum number of variables that are required to be able to define the system. For example, in this system, you need both x1 and x2 to be able to fully define what is the position of the system, what is its velocity, and so on. Let's be a little more definitive in the meaning of degree of freedom. So the degree of freedom, you can loosely define this as the minimum number of variables that are required to fully define the system. Or I guess a system's state, wherein if you want to tell someone exactly what the system is doing, then you need to have information about its position, velocity, and so on. So if you're dealing with just a particle, for example, a point in space, and let's say this is 3D space in which we live, how many variables do you need to be able to define this? So with respect to some reference, you would need to know what is its x coordinate. Let's say this here is x, this is y, and this is z. Then if this here is the point, you want to know what is the distance from the yz plane, that is the x coordinate. You want to know the distance from the xz plane, that is the y coordinate. And you would need to know the distance from the yx plane, that would be the z coordinate. To be able to fully define the system, right? Or wherever is the position of this particle. If the particle is your system, then you need to know what are the x, y, and z coordinates to be able to tell someone exactly where it is. Um, what if now we were trying to locate a point? Right, give me a second. I just want to make sure I'm drawing this correctly. It would have this here, and this point would actually be all the way from here. Okay, so you essentially need these three coordinates. What if instead we were trying to locate a point on this plane of the screen? So let's say this point over here, if you want to define it. Let's say that imagine that you're in a classroom and you have a point on the whiteboard at the blackboard of that classroom. And you now want to tell someone where this point is. How would you do that? Again, you need some kind of a reference frame. So in this case, let's say the reference frame is at this corner of the whiteboard or blackboard, and let's say this is X and this is Y. You then need the distance from the X axis, that is the Y coordinate, and the distance from the Y axis, that is the X coordinate. And with that, you're able to tell someone exactly where it is on this planar surface, perhaps a whiteboard or a blackboard. So this here is a point on a plane. Okay, so this is like it's on a whiteboard, and let's say this is the classroom, and this is one corner of the classroom at the, let's say, on the ground level. And then you want to know the point of, let's say, the projector on the ceiling, and you want to be able to define that by measurements. You need to have three measurements, while if it's on a whiteboard, you just need two measurements. And so you can say that this system over here is a 3 degree of freedom system, while this over here is a 2 degree of freedom system. But let's now consider the case that it's not a point anymore, but some object. Don't sketch what I'm going to do right now, because my drawing requires me to first sketch it along the edges of the paper, and then I'll rotate it. Okay, so give me a second. Don't yet sketch this if you're taking notes on your own. This here is just a cuboid, and this cuboid, it has how many variables do you need to be able to define the object that I've just drawn right now? Think of it as a 3D object. It's like a box that I brought into the classroom, and I want to define exactly how this object is currently. Okay, so let's say again that we're in a classroom and we have a corner of the classroom, the one on the ground, let's say on your left corner. Um, Now, if you want to tell someone exactly how this object is located in space, how many degrees of freedom, or rather, how many variables do you need to be able to define it? I hope that your answer was six. The reason is that to define this object, you would need to first locate it somewhere, and you can locate any point in the object. In general, the center of mass would be located because of certain properties. So you have, let's say, I'm actually going to try and draw it in the same way. So you have the x coordinate, you have the y coordinate, and you have the z coordinate. Okay, so this here is z. Here you have y. So at this point, you have already taken three variables to define the center of mass. Now, you need to also define the orientation. And so, with respect to this reference frame, you could define the angles that define exactly how this is oriented. So if you were to think of this object as your hand, you could have it horizontal with respect to the ground, or you could rotate it in some angle, and you can have essentially a pitch, a roll, or a yaw. So these angles that define it, I'm just gonna sketch with respect to these. Um, this here is the unit vectors of your reference frame, and now you have angles that are associated with the object. This here, and this here, and you will get angles with respect to each. So alpha, beta, gamma. So you need 6 different variables to fully define this 3D object. So you have the x coordinate, y coordinate, z coordinate, and alpha, beta, gamma with respect to the different axes of your reference frame. Okay, so this is essentially the local coordinate system of your body, and then you have angles that define that local coordinate system with respect to the original coordinate system. And so in this case, the number of degrees of freedom is equal to 6. Um, in this case, it was 3. In this case, it was 2. Okay. So often you can obtain the degrees of freedom by just inspection. But in reality, there's also a formula that you can use, which maybe you're familiar with. Um, the number of degrees of freedom is equal to 6r plus 3p minus c. Anyone know what these r, p, and c are? This is for a system. Okay, a system's, I don't need a number here. System's degree of freedom, 6r 3p minus c, where r is the number of rigid bodies, p is the number of particles. These are point bodies. C is the number of constraints. Okay, so rigid bodies require 6 of them, right? Because you have position, 3 for position and 3 for orientation at 6. A particle or a point. So I'm gonna write this also as a particle or a point in space. Okay, so a particle is fully defined by just a point's position. So you have 3 of them for x, y, and z, and then c is the number of constraints. Okay. How can we use that to obtain what we just did by inspection? So in this case, if this is your system, you have 6 times 1 because there is a rigid body, 3 times 0 because there are no particles, c, the number of constraints is 0 because it's fully free to be oriented and positioned in any way in space. In this case, it is 6 times r, where r is 0 because there's just the system is fully defined by just a point, a particle. 3 times p, so 3 times 1, minus c, the number of constraints is 0. So it's 3. Okay, so I'm actually going to write it here. So it is 6 times 0 plus 3 times 1 minus 0. This here is 6 times 0 plus 3 times 1. And now there is a constraint. Can you tell me what that constraint is? It basically states that it must be in the plane of the whiteboard. Okay, so that is a constraint because it prevents any movement out of this plane. So there is one constraint, so minus 1. And over here, it is 6 times 1 plus 3 times 0 minus 0. Okay, let's now look at the case where you have a spring, a damper, and this mass over here. And from the center of mass of this mass, you have a pendulum that is given by m, mass m, and this mass capital M. So this notation here, or rather this lining over here indicates that this surface is immovable. This can move, this can move. Um, so by inspection, can you tell me what is the degree of freedom of the system? First, you must be familiar with these kind of problems where it is drawn as a 2D representation, and so you can reasonably assume that this is going to move only in this direction and this direction. It's not going to go in or out of the plane. It's not going to go up or down. Okay, so it's only going to go left or right. And this pendulum here, because it is attached by this rod or maybe a cable or a string, it is only able to move in a circular path about this point here. So if you had the orientation of this rod with respect to this, well, I should say the angle between this rod and this vertical, that's some angle theta. And if you had the position of this mass m as x, then you'd be able to fully define this system, right? Which means that your answer should be 2 by inspection. Let's now try to do it by uh, the formula. Um, First, we don't care about the orientation of this mass. It maybe can rotate, uh, it can have a pitch, yaw, or roll, but because this was drawn in 2D and this here is fully defined by just this x position and so on, we can instead replace this with just a particle. And similarly, this pendulum here, its orientation, that is the yaw, roll, and pitch, these angles don't matter. It's just going to be going around in this. So we're going to call it, we're going to approximate this as a point. So point approximation or particle approximation for both m and small m. So you now have to think about the constraints, that there are points, and what are the constraints on this on these points. You have one, there is no z motion for capital M. You have no y motion for capital M. X motion does exist. Third one is that you have no z motion for the pendulum gong, that is small m. And constraint 4 is that it is going to be circular motion for the gong m, because it's not that this gong can move in any way in the 2D plane. It has to move according to a circle with respect to the center of mass. Okay, let's now apply the relation. So degree of freedom is equal to 6 times r, which according to a point approximation is 0, plus 3 times number of point approximations or particles is 2, minus the number of constraints is 4. So you have 6 minus 4, that is 2. So the system can be fully defined by 2 variables. Let's now define them. Let's say xm is the x coordinate of the block m, and theta small m is, let's say, the angular position of gong with respect to block. So if I were to now define it, I can say that this here can be theta small m, and with respect to some SEP of this system, let's say this is the SEP, you have xm measured in this way. Okay, so this here would be fully defining the system. Now, what is key is that the number of equations of motion that you will obtain so that you can fully define the system is going to be the equal to the number of degrees of freedom. Why is that? Each equation of motion, that is what we've been obtaining here, see, starting with this one, this defines how x will change with time. Okay, the same with this one. And now when we had the 2 degree of freedom system, you had two equations of motion. When you have these two equations of motion, it defines how both of those variables will evolve with time. So here, this equation says how x1's second derivative, first derivative, zeroth derivative are related to x2's first derivative and zeroth derivative. So this equation defines how x1 will effectively evolve. This here relates the second derivative of x2 with the first, zeroth, and the first derivative of x1 and zeroth. How do these variables evolve with time? Okay, so to be able to fully define the system, the number of equations that you obtain should be equal to the degrees of freedom. Okay, let's now examine the case where you have vertically deflected systems. So we're just gonna, so as we go through this, when we're developing the system equations and so on, I'm slowly gonna introduce newer ideas in the understanding of the, the physical world that we live in. And so I'm gonna try and sandwich both of them together so we can keep expanding our understanding simultaneously. Okay, so vertically deflected systems. It's again using springs and dampers, but now they're oriented vertically. Let's say this is K and this is C. Okay, where do we take our measurements from? There are two possibilities. One is you could take a measurement from the undeflected length of the spring. So option one, measure from undeflected spring length or the natural length. So then this would be your system. What does it mean to say it's undeflected? It means it's not experiencing any forces, and so it says it's natural length. But the problem is there is a force here that's going to be acting on the system. It is gravitational force, right? So this undeflected length will only exist in this configuration if there is no gravity. But the moment gravity exists, if you think of it as just being able to turn on gravity in some way, your system is going to go to a new position wherein the spring has been elongated, and the damper, it only really matters if there is a velocity involved. But let's now look at just a case where it comes to rest at a new position. This new position here is, let's say that the undeflected length is L. This here is L plus delta L. There is the stretched spring length due to gravity. Okay. What is this new position? This here is where it is now in equilibrium, accounting for gravity. This is the SEP position. This here is the undeflected position. Okay, so it's like this before gravity was turned on, this is where gravity is turned on. Okay, let's now look at what is happening here. So you have a free body diagram where you have mass M, you have a force of mg, and what is the spring force? Let's look back at what is the equation that we found for springs. It is k times x2 minus x1, where there's a net deflection from the equilibrium length, right? Um, well, I guess it's better to call this the natural length. Um, Here, when we say equilibrium, it means that the net forces are zero overall, but the Hooke's law means that this force would actually return it to its natural length. It becomes more important when we're talking about vertical systems. So in this case, the net force would be the difference from the undeflected or natural length, which is just delta L. So you have K delta L as the force in the spring. At the static equilibrium position, you have no velocity. That's the meaning of static, which means there's no force coming in from the damper. And so at the equilibrium, because it means that there is no net acceleration, your kinetic diagram will have no force because there is no inertial force mx double dot is equal to 0, right? Because x double dot is equal to 0. So at this position, you now have that essentially x double dot is equal to 0, x dot is equal to 0 by definition. And so you have mg minus k delta L, right? This is, okay, to be complete, I'm going to say this is sum of forces in the free body diagram in the perhaps upward direction is equal to sum of forces in the kinetic diagram. Again, it has to be in the upward direction. Whatever's on the left has to be maintained on the right. You now have that upward is k delta L minus mg is equal to, on the right hand side, 0, which now gives you a relation that says k delta L is equal to mg. So all of this was related to this delta L that took it to the SEP. Okay. Now let's consider the case where your mass has moved to some position further away. So let's say that you're measuring from here, right? And you are now at a position of, say, x, and x is measured downward. So at position x, not SEP, what is your new free body diagram and kinetic diagram? You will have now, you have a spring force of k times x, because x is directly measuring with respect to the undeflected length. And you will have cx dot, because it is possible to have velocity where it's not at SEP. Then you have mg. And so now That is a free body diagram. And in the kinetic diagram, you will have mx double dot. Is it upwards or downwards? It's always dependent on this x direction. So it'll be in the same direction as x, you have mx double dot. In this case, your equation of motion, if you were to do the same, you know, Newton's law, you will have kx plus cx dot minus mg is equal to minus mx double dot, or you will have mx double dot plus cx dot plus kx is equal to mg. Okay, this is your equation of motion. So that was option one, where you're measuring from the undeflected length. So it's like the spring is undeflected, there's no force acting on it, it is massless, so it wouldn't extend in itself. And now you have a mass attached to it, and when gravity acts on it, that undeflected length is changed to this new position, that is a stretched spring length due to gravity. That is where it rests at the SEP. And so we first found this relation for what is delta L at the SEP. And then at a position that's not SEP, that's you've gone further down, maybe it's some force or something, or maybe you uh, extended it downwards and then you just let it go. So there's no real force acting on it, but it's now at some position X, then this is how your system will behave from that position onwards. If there was some force F acting on it, then you would have that force feature over here, and then you will have mg plus F in your equation of motion. Okay. Let's now look at the case where instead of measuring from the undeflected position, you measure from the SEP itself. Okay, so this here is, on the left-hand side, I'm going to say this is undeflected. And now I'm going to draw the same thing, except I'm going to be measuring from the SEP itself. So that's essentially this position here, which I'm trying to draw at the same level as what we drew on the left. Okay, so now we're measuring from the SEP instead. And you have a measurement, let's say it's Y. Okay, so what is the net stretch in the spring at some position Y? Is it equal to Y? Or is it equal to Y plus delta L? So the net deflection in the spring is with respect to the natural length, which is going to be Y plus delta L, right? Because at SEP, it has already extended from its natural length, which was over here, to a position of delta L. And then from there, you're going, extending it further to Y. So the net deflection is Y plus delta L. And so now you have, if I were to draw the free body diagram, so I'm going to draw it here. M, you have mg. Upwards, you have the spring force, which is k times y plus delta L, right? This is the restoring force. It's taking it from its natural position to, well, it looks at the deflection, which is measured from the natural position, so y plus delta L. And what would be the force in the damper? we'd have to differentiate this, right? So it'll be d over dt of y plus delta L. So you get y dot, that is the velocity. And what is the differentiation of delta L? It'll be zero because delta L is a constant. At the SEP, there's a fixed length that determines how far it is from the undeflected length. And that fixed length is, as we found, delta L is equal to mg over k. So you have just that this is c y dot. I hope that makes sense. Okay, so what about the kinetic diagram? You then have my double dot, which is in the same direction. So it's this way, my double dot. And so now if you were to apply the, well, I guess to keep it consistent side by side, I'm going to move this here, right? You now have k times y plus delta L plus cy dot minus mg is equal to my double dot. What do we notice here? We had that k delta L minus mg is equal to 0. So k delta L minus mg is equal to 0. That delta L here, it's independent of the coordinate x, right? It's just talking about the system property where it comes to rest from its undeflected position. So you have k delta L is equal to mg, which means I can cancel these out. So in this case, you have ky plus cy dot is equal to my double dot. Well, I guess I made a mistake here. This should be minus my double dot. If I were to move this around, you will get my double dot plus cy dot plus ky is equal to 0. This here is your equation of motion. So what do we observe? In systems where the springs are vertically deflected, measuring from the SEP results in an equation of motion that does not feature the gravitational term. The reason is that at the SEP, the deflection in the spring has already absorbed the force due to gravity, right? So you see that over here. From the undeflected position, there's a restoring force that cancels out the gravitational force. So k delta L cancels it out. If you move further from that, if you're measuring from the undeflected position, that x includes the delta L. And so you will result in an equation that has mg to account for that, while instead if you measure from the SEP, your y is starting from a position where the mg term has already been cancelled out, and so you will then get this as your equation of motion. So here, if you were to try to find the equilibrium, what do? For the static equilibrium position, this is 0 and this is 0, which gives you y is equal to 0. On the other hand, if you're measuring from the undeflected position and you're trying to find the equilibrium, this goes to 0, this goes to 0, and then you get x of your equilibrium is equal to mg over k. Okay, I hope this makes sense. Worth noting is that this is only true where the deflection of the spring is along the vertical direction. So when the spring deflection is in the vertical direction only, the gravitational term forces are cancelled by static deflection in the springs. So looking at how it was derived, you have this static deflection that's canceling out the gravitational force. If it happens to be that it is not vertically deflected alone, for example, in this springy pendulum, then you cannot use this result because now your deflection is radially outward, right? And so that static deflection is not going to cancel gravity in the other positions, and so you cannot use this result. So if you're in doubt, include gravitational forces and static deflection forces, and then see if they cancel out and so on. Okay, so I'll just write that as a note. Cannot use this um, in case of a springy pendulum. And if in doubt, include gravitational forces and static deflection. So let's now apply this in another example. In this case, I'm going to draw two masses. One spring here and another spring here. And here's one mass, M, let's say M1. And then you have another mass of M2 here. And between the two of them, there is a damper given by C. This here is K1, this here is K2. And let's say that with the ground, there is another spring that is K2. Okay, so the first thing when you're trying to obtain the equation of motion is you're trying to see what is the degree of freedom. In this case, how many equations of motion will you obtain? So this one can move independently of this one, right? So this can have some position x1, this can have some position x2. The thing is, where are you measuring it from? Are you measuring it from undeflected or SEP? Now, let's do it for both cases where you have first undeflected. So we're first going to do it for the case where this here is an undeflected position. This here is an undeflected position, which means that this is before gravity is begun to act, or all the springs are in their natural lengths. Okay. Let's also add a force here to make it interesting. So this here is, let's say, F2 of t. Okay, and I'm going to say that this here is x2 and this here is x1. So we're trying to obtain the equation of motion. We're doing option 1 from the undeflected position. In your equation of motion, will you have the gravitational terms or no? Let's find out. So in this case, spring 1, if it has moved from this undeflected position by x, what is the net force in the spring? It will be Fs1 is kx1, because this x1 is directly measuring it from the static deflection. Sorry, it's directly measuring it from the undeflected position. And so this here is going to be in elongation for positive x1. What about spring 2? For positive x2, you will have Fs2 is equal to K, well, the first one should have been K1. So this here is K2 x2, again in elongation. And for spring 3, for positive x2, you have Fs3 is equal to, you will have K2 x2. This should have been K3. Apologize. This is K3 x2, the same x2, but in this case it would be in compression. What about the damper? Now this damper is between M1 and M2, which means that it's dependent on x1 and x2. So let's now say that if x1 dot is greater than x2 dot, you would have Fd is equal to C times x1 dot minus x2 dot. And it's basically saying that the velocity of this is more than the velocity of this. So in this case, it would be in compression. If instead you chose x2 dot greater than x1 dot, then what would you have? You would have x2 dot greater than x1 dot. This velocity is more than this velocity. And so this would be in tension. And your force would be x2 dot greater than x1 dot. Okay, so you could choose either. As you can see, this tension or compression part, it counters whatever is your assumption. So it accounts for whatever is your assumption. Okay, so now we can draw the free body diagrams. Again, in this case, let's draw it as an exploded view. You have this spring here, you have this mass here, you have this damper, and then another mass here, and then a spring. And don't forget that there's another spring over here. So here you have Fs1, Fs1, Fd, Fd. So I'm drawing it according to what I've defined. Here you have, this one is in compression, so this is being compressed. So you have the reaction force as shown. There's Fs3. And this one is in elongation, so it's in tension, Fs2. And this here is Fs2. And now you have to account for all the external forces. So there is mg, well, actually it's m1g. This here is m1g. And you have here m2g. And you also have that F2 of t over there. Okay, are there any forces we're missing? We've accounted for this, 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 this. We have the gravitational forces on both, and then we have the external force F2 of t. This here is a set of free body diagrams, and now let's draw the kinetic diagram. So this here has inertial force in the same direction as x1, so you have m1 x1 double dot, and then you have m2 coming in with m2 x2 double dot. And if you were to now write down the Newton's law, so sum of force in the free body diagram, let's say I do it for the downward direction as positive. That's for the first object. You now have, carefully list all of them. So you have m1g plus Now FD, you can write it as C times x2 dot minus x1 dot. And then you have FS1. This is in the opposite direction. So you have K1 x1. And that's all of the forces. And then you have that this is equal to M1 x1 double dot. So if you now rearrange the terms, you will get M1 x1 double dot plus C x1 dot plus K1 x1. So I've moved this and this to the other side. And now if I move this one to the other side, you will have minus C x2 dot, and then this here remains. So you have M1G. So this here is one equation of motion. Okay, and then next you have for the second object, let's say in this case, I choose to do it upward. All that matters is that it has to be in the same direction for both sides of the equation. So upward, you have FD, so that is C x2 dot minus x1 dot, plus you have FS2, which is K2 x2, and then downward you have F2 of t, M2g, and then you have upward again Fs3, which is K3 x3. All of this is going to be equal to minus M2 x2 double dot. If I now move it to the other side, you will get M2 x2 double dot plus C x2 dot plus K3x. Then you have the other terms minus C x1 dot. There's no x1, so this would be equal to, and on the other side you have F2 of t plus M2g. So these are the two equations of motion. If you're going from the undeflected position, as you can see, M1g and M2g do feature. If, on the other hand, you choose to measure from the SEP, so the same system, I'm just gonna measure it from the SEP now. So this here's a SEP. I'm gonna name this as Y1, Y2. Okay, so you have to now take into account the fact that at the SEP, the static deflection in this spring, in this spring, and this spring, they're all accounting for the gravity, the gravitational forces that are acting. Okay, so if we were to now sketch at SEP, you have this mass M1. It has a downward force of M1G, an upward force of, let's say, F1 static, which is equal to K1 delta 1. We don't have to account for this because at SEP there is no velocity, and so there's no damping forces involved. For this mass here, that's M2, you have gravitational force downward of M2G. Then upward you have F3 static, which is equal to K3 delta 3. And upward again, you have K2 delta 2, which is F2 static. Why is it upward? It's because as gravity acts, this will be pulled downward, and so this will be in elongation. Why is this upward? As gravity acts, this pull downward, and this spring would be in compression, so it's acting upwards. Okay, so at the SEP, since the net inertial forces are zero, you have then that K1 delta 1 is equal to M1G, and K2 delta 2 plus K3 delta 3 is equal to M2G. Okay, now let's look at the case where it has moved from the SEP. And so now you have in spring 1, you will have a total deflection from the natural length of delta 1 plus y1, and the restoring force will be K1 times that is going to be in tension. And you have Fs2 as K2 delta 2 plus y2, again in tension, and Fs3 with K3 delta 3 plus y2, except now this is in compression. And then you have Fd being equal to, if you have y1 dot greater than y2 dot, then you will have y1 dot minus y2 dot. If y1 dot greater than y2 dot, and this would be, so this velocity is more than this velocity, so this would be in compression. Okay, I guess we can write this for positive y1, for positive y2, for positive y2. So with this, we can now draw our free body diagrams. In this case, you will have M1, you have Fs1, and this damper is in compression. So this is experiencing forces inward, which means this would be experiencing Fd in this way. For mass M2, again, this is in compression, which means the reaction force would be downward. So you have here Fd. What about the spring that's acting? This spring is in tension. So you have Fs2 here, and this one is in compression. So you have Fs3. And don't forget that you have an external force of F2, M2G, and here again you have M1G. In terms of the kinetic diagram, you will then have M1 Y1 double dot in this way, M2 Y2 double dot in this way. And as a result of this, you will have an equation of motion obtained from the sum of free body diagrams along the, let's say, upward direction being positive for 1 is equal to sum of free body kinetic diagrams for 1, say upwards in this way. This will now give us Fs1 minus M1G minus Fd is equal to M1 Y1 double dot, except that Fs1 is K1 delta 1 plus K1 Y1, and then you have minus M1G minus Fd is equal to M1 Y1 double dot. And we had this relation here which says that K1 delta 1 is M1G, so these two cancel out. And you get as a result M1 Y1 double dot. And I guess I could have written here Fd as, well, I'm just going to write it here now. Plus Fd, where Fd is C Y1 dot. That is going to be minus C Y2 dot. and then plus k1 y1 is equal to 0. So this here is your equation of motion. And then for the second block, you then have the sum of forces in the free body diagram of 2. I'm going to keep it as positive upwards is equal to the sum of forces in the kinetic diagram for 2. Again, positive upwards. And if I now write down all those relations, I will have Fd downwards, so negative, plus Fs2 minus F2 minus M2G plus Fs3 is equal to minus M2 Y2 double dot. I guess I made a mistake here since that this here was positive, right? So I should have written minus, and then it is when this comes on the other side that I get this. Okay, just uh, catch those kind of mistakes. So now if I substitute the values, I have minus C times Y1 dot minus Y2 dot plus Fs2 being K2 times delta plus Y2 minus F2 being, well, this is Fs2. No, F2 is the external force. So F2 of T minus M2G plus Fs3 being K3 times delta 3 plus Y2. I'm going to set this equal to 0, and I'm going to put M2 Y2 double dot on the left hand side. So now if I collect the terms, I will get M2 Y2 double dot plus C Y2 dot plus K3 X2, well, K3 Y2, sorry, minus C Y1 dot, and then I have K2 delta, and this here should be delta 2. K2 delta 2 plus I will have K3 delta 3 minus M2G is equal to F2 of T. What you see here is that these terms will cancel out because of this relation here, which now allows me to write my final equation of motion as M2 Y2 double dot plus C Y2 dot plus K3 Y2 minus C Y1 dot is equal to F2 of T. Okay, and so you have now two equations of motion. You see that there is no gravitational force that features, and the reason is that at SEP, the deflection in the spring was already accounting for that gravitational force. As a result, you can end up either doing these kind of steps where you fully define what is the net deflection, or you can just ignore this so long as you don't write the mg terms. Okay, and so that is one way of doing it. Another way is like have this termed as F1 ST, this term is F2 ST, this term is F3 ST, and then you will have mg and F1 ST over here, and they will cancel out. Here you will have F2 ST and F3 ST canceling out with M2G. Okay, so you can do it in any of these ways. In the end, your SEP related equations of motion should not be including a gravitational term because that would already have been cancelled for. Okay, so keep that in mind. Depending on the way of measurement, you will either have mg as an external force or you will not have it. From the undeflected position, you will have mg. From the SEP position, you will not have mg. Okay, so these are the two equations of motion that you obtain based on your measurement of the system. Okay, I hope all of this makes sense. Let me know if you have any questions.